Alright everybody, welcome back. This is our third video for section 6.9, Integrating Using Substitution. It's actually the second video on the Integrating Using Substitution Part 2 lesson. So we're going to continue on, pick up right where we left off with example 5 here. Now up to this point, all of the examples we've done using integration by substitution have been examples where we've been finding indefinite integrals, but we can use substitution for definite integrals as well. And the process is generally the same, except for we need to now worry about handling these limits of integration in the definite integral. So what we're going to do is we're going to start off the same way we do in general when we're using substitution. We look for what we think is the best substitution. And in this particular example, I think that's going to be u equals 2 cubed, or t cubed minus 1, since that's inside of the other function. And then I find my du. Du is equal to 3t squared dt, which is very close to what's left when I make my substitution. So in all reality, I just need to replace that with a 1/3 du. Okay, so I can turn this integral into the integral, or pardon me, 1/3 times the integral of the square root of u du. Now I have one more step here. These limits of integration are t-values. So what I want to do is I want to change them into u-values. So here's how I'm going to do that. When t is 2, u is equal to 2 cubed minus 1. All I'm doing is substituting the value of 2 in here for t and calculating the value of u. So that's going to be 7. And then when t is 4, I approach it a very similar fashion. U is going to be 4 to the third minus 1, which is 63. So those are my limits of integration in terms of u. And now from here, I can just go ahead and take the antiderivative. That's going to be 2/3 u to the 3/2. And we're going to evaluate that from 7 to 63. So this is 2/9 u to the 3/2 evaluated from 7 to 63. So it's 2/9 times 63 to the 3/2 minus 2/9 times 7 to the 3/2. And if I wanted a decimal, I could go ahead and punch that up, but I'm okay leaving that as the exact value. All right, example 6. U equals the sine of x is our best substitution. So du is cosine of x dx. That works out perfectly. This turns into the integral of u du. And then I need to change my limits of integration. When x is 0, u is the sine of 0, which is 0. And when x is pi over 2, u is the sine of pi over 2, which is 1. So this turns into the integral from 0 to 1 in terms of u. And now I'll go ahead and find my antiderivative. Again, that's going to be 2/3 u to the 3/2, which we're going to evaluate from 0 to 1. So I've got 2/3 times 1 to the 3/2 minus 2/3 times 0 to the 3/2, and that's equal to 2/3. Okay, example 7. It's not apparent, just looking at this, that this is a substitution problem, but it is. Tangent of x is equal to sine of x over cosine of x. And so I need to make a substitution. Choices here as far as substitutions go, I could use u equals sine of x, or I could use u equals cosine of x. In general, when you have a fraction, it's better to work with your substitution being something that comes from the denominator. So I'm going to try u equals cosine of x, and then du is negative sine of x dx. So I can replace, and this substitution indeed is going to work out okay for me. This is going to turn into the opposite of the integral of du over u, which is the opposite of the natural log of the absolute value of u plus c. And then I bring my u back. And there's my integral. Now, if I had tried to use sine as a substitution there, when I took du, I would have had du equals cosine of x dx, but that cosine is in the numerator with the dx, whereas in this problem the cosine is in the denominator, whereas the dx is in the numerator. That's why u equals sine of x would not have been a good substitution there. All right, last one. All right, integrate the integral of 1 over x natural log of x dx. And I just said that it's a good idea a lot of times to use the fraction of the denominator of a fraction as a substitution. Unfortunately, that's not the case in this one. Now, if you think back to the derivatives you should know that the derivative of natural log of x is just 1 over x. So it appears that u equals natural log of x would be a perfect substitution here, because du is 1 over x dx. That gets everything else. And this can be rewritten as the integral of du over u. We take the integral, that's natural log of the absolute value of u plus c, and then we bring our u back, and boom, there's our answer. All right, that's the end of this video, and the end of our integrating using substitution part 2 lesson. We're going to come back in part 3 and do some trickier substitutions than these. So we'll see you then. Have a great rest of your day, everybody. Bye-bye.